speaker. Next speaker is Julian Fritsch from the Idiap Martigny in Switzerland.
Do I see my slides here as well? Just there? What's with this? Is no screen? Oh, okay. Okay, so this work on modeling glottal source information for phonation assessment in Parkinson's disease is a TAPAS project collaboration between Camilo Vásquez-Correa from Erlangen-Nürnberg and PC Guitar Lab in Medellin, and myself from Idiap and EPFL. I structured the presentation into a description of Parkinsonian speech or hypokinetic dysarthria, as it is often referred to in the literature. I will explain how we are proposing to model glottal source information, and we are validating that in experiments and show some results and conclusions. Now, in the context of Parkinson's speech, intelligibility is decreased due to the symptoms of Parkinson's disease, such as rigidity of muscles. And that can happen in the phonation aspect, so in the vocal cords, in prosody, or in articulation and nasality. And in the context of Parkinson's disease, that has been studied, the articulation dimensions have been studied with generic speech features, such as MFCCs, form and frequencies. You might know the work on vowel space area or voiced onset time. In the context of prosody, features such as F0, jitter, shimmer, energy, voiced and unvoiced ratios have been studied. However, in the context of phonation, there has not been any work, which is why this is an initial study on how to do so. Now, one known fact about glottal source information, so the rate of vocal fold oscillation is largely determined by subglottal pressure coming from the lungs. So the hypothesis that we are working on is that the increased rigidity of vocal folds affects the glottal signals, but you cannot obtain such a glottal signal non-invasively, which is why we propose to use filtering techniques to obtain different glottal signals and analyze those glottal signals. Now, on the filtering techniques that we're selecting, we took two that fall under the category of glottal source reconstruction. The first one, iterative adaptive inverse filtering. As the name says, is an iterative scheme based on linear prediction to remove the vocal tract information, and it also removes attempts to remove lip radiation. Secondly, we use glottal closure opening instant estimation forward-backward algorithm, short GEFBA, which operates by first obtaining a rough estimate of the source signal and then doing a more sophisticated inverse filtering on the per pitch period. And thirdly, we're using zero frequency filtering, which is based on the idea that the glottal closure generates an impulse-like excitation, therefore everything else can be removed with a cascade of 2 0 Hertz resonators, and then you also do a trend removal operation on that signal. Now, you can use all of these three filtering techniques to obtain, to mark the glottal closure instance. They're marked in the plot here with the blue dots. And we're also plotting the raw waveform. Now, based on these signals, we are extracting features. So from the raw and zero frequency filtered signal, we are extracting a feature set which we name perturbation features. There are 7 frame level features, so first and second derivative of F0, a jitter shimmer, amplitude perturbation coefficient, pitch perturbation coefficient, and logarithmic energy, of which we compute 4 functionals: mean, standard deviation, skewness, kurtosis. That ends up being a 28-dimensional feature vector per utterance, which we later will plug into a support vector machine with a Gaussian kernel. The feature extraction is available on GitHub. You can see the link on the bottom, but it's also in the paper. Now, from the glottal signals, we extract a feature set we call glottal features from the IAIF and the GEFBA signal. There are 9 features, and roughly they are characteristics of the glottal closure instance, such as their intervals and amplitude, and characteristics of the glottal signal itself, first and second harmonic, for example. Again, of those 9 frame level features, we calculate functionals and end up with a 36-dimensional feature vector that we again plug into SVM. Now, we also propose to use raw waveform convolutional neural networks. And in this case, we are using a first filter length of 2 milliseconds, which is less than a pitch period. Input to the networks are 1 second signal chunks, and in the case of classification, we use a cross entropy loss and mean squared error loss for the regression task. Now, to that network, you can feed any signal. So you can feed the raw waveform or any of the filtered signals, and that goes through a filter stage of convolutional layers with max pooling and ReLU, and a classification stage where you end up with a score per frame that we then average to get a score per utterance. Moving on to the experiments that we conducted. So we work on the PC-GITA dataset, which has 50 Parkinson's disease patients and 50 control subjects that all speak Colombian Spanish natively. And out of the dataset, we only took the tasks of sustained vowels and diadochokinetic tasks. And the labels we are working on is dysarthria scale, which is where speakers are evaluated on 13 aspects, of which some are lip movement, palate and velum movement, monotonicity, but they were also evaluated on breathing aspects. So the first label that we are using is called breathing capacity, is a range from 0 to 4, as well as the breathing duration, also ranging from 0 to 4. Now, since this is dysarthria scale, low value or 0 means no impairment, and a high value means high impairment of breathing capacity and duration. We are also looking at the global breathing impairment score, which is a sum of the two, therefore ranging from 0 to 8. And we do our experiments in a 10-fold cross-validation, and we do classification and regression. So in the case of duration impairment and capacity impairment, we do a classification between low impairment and high impairment, so 0 to 2 versus 3 to 4. And in the case of the global breathing impairment, we are doing a classification between low, which is 0 to 4, versus 5 to 8 in that scale. And of course also the regression of all the labels. Regarding the results, so in this table I once put all the experiments that we conducted. So on the left you can see the signals. So you can see raw waveform, IAIF, GEFBA signal, and ZFF signal. And In the next column is the method that we're using, so perturbation features, glottal signals, CNNs, and we're evaluating accuracy and F-score. So I highlighted the best results which we received with the ZFF filtered signals and perturbation features, reaching a performance of 79%, and CNN with ZFF filtered signals an accuracy of 70%. I shortened the results here for breathing capacity. We reach up to 84% accuracy. However, as you can see, generally the CNN network is performing less good than the features classified with SVM. And for the regression results, again, we have the signal and the method in the table. However, I only put the best results here. So we're evaluating in terms of Pearson and Spearman's correlation, as well as mean average error, and again the perturbation features plus the support vector regressor work best. We observe a correlation of 0.65 in the case of breathing duration, and similarly for the breathing capacity. However, this time only the vanilla raw waveforms were good enough. And in the case of the global breathing impairment, again, the perturbation features work best with a correlation of 0.7734. In terms of mean average error, you can see that we have, for example, for the global breathing impairment, we have an average error of 1.4, which means that for every estimate that we make on a range of 0 to 8, we make an error of 0.4. And I've plotted this also in a scatter plot. So on the x-axis, you see real global breathing impairment. On the y-axis, predicted labels. So you can see that the predicted labels only range from 1 to 6. So we're kind of not predicting any zeros, and overall also under predicting, which is why the regression line is also rather flat. Now to my conclusions. So we propose to estimate the severity of breathing impairment. We observed that the functionals of perturbation features give the most robust estimate, and overall we had a classification of breathing impairment with up to 84% accuracy, and the regression of breathing impairment with Spearman's correlation of 0.74. Thank you.
Thank you. There is a question online.
So there's a question. Thank you for your sharing. I have a similar question to the previous one. How do you decide the acoustic features? Are there any difference between solving disordered speech problems and other speech tasks in choosing features?
So this is the features that we use here are features that have been used for Parkinson's detection before. They're not exclusive to the problem. So this is what we investigated, but
if I may ask it further. So one thing I noticed is that for some CNN models, you had pretty good accuracy and very, very, very bad area under curve. So like 70% accuracy and 0.3 AUC. And you had a balanced class distribution. So I wonder how it is possible.
By area under the, I think we reported F-score.
Oh, yeah, that's right, F-score. So the F-score, yeah, okay, and the F-score is okay. It's bad in this way because it's easy to get 7%. And I have another question before the audience. So I was wondering what can be treated as a baseline. So because you had actually two proposed methods, but no baseline. So
yeah, that was part of the introduction, right? So there has not been any previous work on doing that. So this is kind of the baseline.
So no MFCCs or any.
No, we did not try. No. Maybe we could have investigated that as well.
Thank you. Is there any question from the floor? Anyone? We do have an online. Khalid, first. Oh yeah, okay.
We have 4 minutes.
We have 4 minutes, so it's time enough. So Khalid, if you could please. Yeah, it's.
The camera cannot see you. You can stay there.
If I knew, I would. Actually, to be honest, I didn't get because glottal features are known to be extremely important for assessing dysarthria. There is no discussion or doubt about it. The only problem is how to reflect that, to find the features, to capture the impairment in the glottal flow. So I didn't get what is the contribution of this feature that you have computed in whatever the classification or the regression, because you have compared many features, and it seems that the perturbation measures are giving the best scores, but me really, I don't care about this percentage, but just to see what is the contribution of glottal features computed the way you compute them for the classification or the regression.
Well, I think the point of the paper is that we are not exactly assessing dysarthria, but these breathing parameters. So, I mean, they have been used for dysarthria assessment, but not for the breathing. So we are not actually measuring anything that is in the speech, but the breathing.
So the point is that you are using glottal features, you are assessing or defining some kind of breathing cue or breathing feature.
Some questions from the internet.
Yeah, we have like 2 minutes for the two overall. Can you explain the data used in training? For example, what was the average length of utterances for Parkinson's disease and not Parkinson's?
I guess they would not differ that much between healthy and Parkinson's, but I would say, I mean, sustained vowel, that is probably somewhere between 3 and 5-6 seconds. Similarly for diadochokinetic task, probably a bit longer the diadochokinetic task, say 5 to 15 seconds, I would say. And overall, the amount of data was, if I remember correctly, like between an hour and a half.
For the 100 speakers combined?
Exactly.
Okay. And yeah, one question for 1 minute. Your hypothesis was based on rigidity of vocal fold movement. Would this limit your choice of features? Would PD cause incoordination in vocal fold movement?
Can you repeat it? Sorry.
So your hypothesis was based on the rigidity of vocal fold movement.
Mm-hmm.
Would this limit your choice of features? Would PD cause incoordination in vocal fold movement?
I mean, the features, it kind of limits it because, for example, as we said earlier, MFCCs are not really related to the fundamental frequency, but to the vocal tract, which we are not really interested in. So, yeah, rather like pitch-related features would be better.
Okay, I guess.
Yeah.
Okay, thank you.
Thank you.